and gentlemen, it is my pleasure to introduce our first industry keynote speaker, Ms. Jen Sovada, President of the Global Public Sector for Sandbox AQ, Associate Professor at Georgetown University's Quantum Information Sciences and National Security Curriculums, and Chairwoman of the Board of Directors for the Defense Entrepreneurs Forum. Ms. Sovada has previously served as Chief Futures Officer, Senior Vice President, and General Manager for Mission Tech Solutions. With 25 years of experience in the Air Force's intelligence communities, Colonel Retired Sovada commanded the Air Force Technical Applications Center, the Department of Defense's sole organization for nuclear treaty monitoring. Please welcome Ms. Sovada for her keynote address.
Well, good morning, everybody. And I'm really excited to be here today to talk to you about the promise and threat of quantum technology for logistics. So just a show of hands, how many people out there are quantum physicists? Anyone? 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 Maybe one, maybe not. But how many of you want to continually try to find ways to improve logistics? And that should be everybody in the room, right? We all want to look at how do we do things better? How do we do things more smartly? How do we make an impact with the technology that is out there, but also understanding what the capabilities are we currently have today? So that's what we're going to talk about. And why is this important? One of the reasons, if we think about it, the race to the moon for Project Apollo, over a 13-year period, they spent $25.8 billion in today's dollars for that. But in quantum technology, in about the last 5 to 7 years, there's been $36 billion spent on quantum. And so you put that into perspective, a technology that's not even getting us to the moon has exponentially more money being spent on research and development and trying to operationalize capabilities. And this is even more important when we look at it in relation to the national security imperative that we have today. So Pan Zhongwei is the leader of the People's Republic of China's quantum program, and he is known as the godfather of quantum. And his goal is to take as much as he can out of the quantum information space and use it back in China in order to advance the Chinese quantum capability. And you may think, well, that's okay. We all want to learn, we all want to grow, we all want to learn what we can do with the technology to improve, enhance, and support the missions that we have. But the difference is that he has two main aims of his quantum project. The first one is to build an encryption cracking quantum computer. So a computer that can crack all modern cryptography today, all of your encryption. So if you think about it, you log onto your computer at work, put your CAC in, but the certificates that are on your CAC are no longer secure. The second thing he wants to do is to build a global and then a national and then global network to secure communications to keep them protected from any outside interference. And right now they have about a 10,000 kilometer network in length on the eastern shore of China. And the last but not least, if you look at it, over $15 billion of government funding has been spent in China on quantum alone. If you think back to the number I just showed you of $36 billion, it's almost half is coming from the People's Republic of China alone. And they've created a Quantum Manhattan project where there are about 2,000 total engineers who are working on trying to crack quantum computing and figure out how to make it as effective as it can be. And Pan Zhongwei is sort of like the Robert Oppenheimer of the quantum program within China. Yin Hao is the General Leslie Groves, who's sort of giving the guidance and the funding. And together, the three gentlemen up here provide the guidance and the leadership as to what should be happening within China's quantum program. They then share that, and the research organizations as well as the universities really focus on the technologies that are most important to China. And then that technology is shifted to the small businesses, which are mostly run by people within the quantum enterprise on the government side. And then it's sent to the larger industrial organizations and companies, such as KSIC, which is in the middle here on the left. And that's an organization very similar to a Raytheon, a Lockheed Martin, Northrop Grumman, that builds weapons, space systems, missiles, aircraft, and many other things. And the goal is to combine quantum technology with those weapon systems. And surprisingly, Russia's doing it too. They're building a quantum Manhattan project, and Putin has actually stated that he wants compatriots to come to Russia to work on the quantum program. One little stipulation, you have to want to become a permanent resident of Russia. Maybe you want to do that, maybe you don't. But the goal is to really emulate what the Chinese are doing and building upon the quantum capabilities that they can partner together with as a Russia-China stronghold in the quantum space. So you may be saying, okay, that's interesting, but I have no idea what quantum is. So what we're going to do now is we're going to talk about what is quantum and artificial intelligence and how that enables quantum and how quantum enables AI. And we're going to talk about it as it relates to logistics. So the first thing we need to know is, what is quantum? Quantum is really the most basic piece of modern physics today. All of us who learn Newtonian physics growing up, that's actually not really how physics works. Physics is really looking at the biological behavior of matter and energy at that subatomic particle level. So our bodies are quantum physical systems, believe it or not. And what we do now is we take the world of bits, artificial intelligence, and what we do today with our current computing, and we also enable that with the world of atoms, which is quantum physics. And when we combine those together, we get a very powerful and impactful grouping of technologies that enable us to train data better, analyze data better, and create new tools that will enhance and accelerate the technologies that we need and are looking to create. And they're created with these things called qubits. So we've all heard of a bit. A bit is a 1 or a 0. It's either on or it's off. It's yes or it's no. And they're stored in your memory as either that 1 or a 0. But a quantum bit is used to store information that is a 1 or a 0, or it could be any combination therein. And that combination is called superposition. Okay, why does that matter? We're actually in the third quantum revolution. How many of you realized that the first quantum revolution started in the early 1900s with the identification and the theory and the foundation of quantum technology and quantum theory? And then we move into the 1950s and we look at lasers, MRIs, transistors. A lot of the technology that we use today, that it's part of our computers, a part of our TV systems, even our communication systems, are all built on quantum technology. And today, this third quantum revolution is really about engineering at scale. And how do we look at problems a little bit differently so that we can have quantum computing, quantum sensing, as well as quantum security and communications. And so what we're going to do is we're going to walk through the 3 legs of quantum information science and talk about how each of those has applications for logistics. The first one we're going to look at is quantum computers, which also includes simulation at the quantum level. Okay, here we go. So quantum computers are really a paradigm shift in reality. And why is that? It's because it's an exponential increase in processing power. Right now, we cannot realize and don't understand the level of increase that we will see in that processing power. And it works in a different way, because what it does is it enables us to model very complex systems, whether they're at the biological level, they're at the material level, and looking at how molecules interact with each other. This can have widely ranging applications, especially when we look at things like accelerating drug discovery, modeling different types of transactions, whether it's thinking of logistics transactions. How many logistics transactions happen daily on either delivering information, delivering capabilities, or movement of vehicles, ships, airplanes. And then the last thing it can do is it can help us to secure our IT infrastructure by enabling advanced capabilities such as quantum key distribution and quantum random number generation. Quantum computer does harness those properties of those quantum states and enables you to process things faster. Two things that you need to know. One is superposition. This is what I talked about, that the ones and the zeros are happening simultaneously. And the other thing is called entanglement. And that's when two qubits know the information and the states of the other qubit. And what that does is it helps us to grow exponentially in the amount of data that we can process. All right, there's 5 or 6 main types of quantum computers. They're not mature enough to be operational at this moment, but they're continually being updated and upgraded. And people anticipate that quantum computers are going to be around in the 2035, 2040, 2050 timeframe. But what we're seeing at this moment is an acceleration of that quantum technology almost on a daily basis. So people thought initially 2050 was where we were with quantum computers, but that is starting to inch closer and closer and closer together. But until those quantum computers are around, we can do something called simulation. And what is simulation? It's the ability to take what you think is going to be happening in a quantum realm and simulate it today. And we can look at this from life sciences, as I mentioned, those biological systems, drug discovery. But then the two that are more interesting to logistics are chemicals and materials, developing advanced materials, as well as maybe new batteries that are better, batteries that are more efficient, and then finally, logistical operations. And we'll talk about those as we go forward. So the first thing that we want to do is simulate the applications for logistics. And once quantum computers are here, we can just migrate those applications over to quantum computers. And if you look here, supply chain management, such as route optimization, cargo packing optimization, as well as materials development and battery development, are really impactful for logistics. First off, we'll talk about supply chain management. Route optimization, if you can take all the weather data that's in the world, the water currents, the weight of what you're trying to transport, as well as other many complex ecosystems, put all of that data together and simulate all of the possible combinations of what could happen, your systems continually learn. And through that learning, you can get to a route optimized for what you're trying to achieve, whether it's in the air, whether it's on the ground, whether it is on the sea. You also have improved disruption management, where you now take all of the events in the world, whether it's weather events, hurricanes, wars, natural disasters, and you pull that together, and now you can think about what are the conditions, and that can be simulated to enable you to understand where you might have disruptions in your logistical systems, where you want to try to avoid those disruptions, and ways that you can possibly change the course of things that may happen. And then you can also faster re-optimize. We know that sometimes events happen that we don't anticipate. And so how do you re-optimize your route without having to waste too much time, too much fuel, or people's time? From a cargo optimization perspective, we want to make sure that we limit loss, optimize for weight, increase the speed of loading and unloading. Think if we're going to war and we need to get logistics someplace quickly, that how quickly we can get there, as well as how quickly we can unload and load, impacts our effectiveness in warfighting. We can also talk about more precise demand. One of the things that you go to the store, or you go to the chow hall and you get your food and you realize like there's no milk. That's because maybe logistically that wasn't optimized. They didn't think about that. And then finally, we can increase sustainability. We can reduce carbon emissions, reduce gas usage when we have better routes and optimization of that. And you'll see at the bottom of the banner that even a 1% increase in performance in that last mile of delivery. So this isn't even the entire chain of routes or optimization or logistical transport. You can have $400 million annually saved worldwide. So then the other thing that we need to think about is materials and what our transportation is made of. A lot of the devices that we're carrying are heavy, whether it's a tank, whether it is helicopter parts, it doesn't matter, it's all heavy. As well as the ships themselves or the aircraft themselves that are transporting things back and forth. We now can look at how do we optimize and change and develop new materials that look at all of those target categories of their properties, their performance, how they impact the environment, if they're toxic to humans or the environment, and the cost. And develop new materials and new chemicals that enable us to carry the same amount of weight, but be lighter, be just as survivable, and possibly be more economically or ecologically friendly and economically friendly, as well as the things that go into all of those logistics, whether it's an aircraft or a ship. And the way that we do this is that you take the top of the funnel and say, what are all the combinations that are out there and the compositions, and you process the conditions of what you're looking for, whether it's less weight, more survivability, more economically friendly, more ecologically friendly, and then you start mixing things together with high computational rates. And then at the bottom, you come out with capabilities and molecules that have been combined together that you can now test in a laboratory, instead of having to start with all laboratory tests that take time and waste resources. Then if we also look at battery improvements, DLA procures $200 million in batteries every year. What if we were able to build better batteries? Right now, we don't know the life cycle of a battery, how long it's going to last, until it has finished its life cycle, sitting on a shelf or being used. We don't know how the environment impacts that length of that life cycle, if it's too cold or if it's too hot, or if it's been in a different type of environment, how is the life cycle affected? We now can take batteries and simulate that by taking all the information that we have about battery optimization, battery performance, and tell you how a battery will perform. We can also explore options for using other materials besides lithium, rare earth minerals, and other things that are in contested environments that will enable you to develop new batteries without relying on them. And one of the most important things is being able to decrease the weight of batteries. If we can develop batteries differently, we can decrease the weight while increasing survivability, while increasing lifespan, life cycle of batteries. Can you imagine as a soldier not having to carry 50 pounds of batteries with you in addition to all of your other equipment? So overall, being able to simulate helps you to increase your maneuverability, your survivability, and the predictability, all of which are important to logistics. We can optimize our supply chains, we can build alternative composite materials, and then optimize battery performance and develop new batteries. So now that we've talked about simulation and quantum computing, we're going to talk about quantum security and communications. First thing is quantum communications. So question for everybody in here, who use encrypted apps? iMessage, Signal, WhatsApp, Proton Mail. I bet almost everybody does. If you're using an iPhone, you're using encrypted applications. If you're using email, you're using encrypted applications. So this touches everybody, encrypted messages. But what's happening now is that the weaponization of cyber continues to accelerate. And when you add that into having a scaled quantum processor, the security risk is even higher than what we experience today. And there are things happening on a daily basis called store now, decrypt later attacks. And what happens is that an adversarial nation or a bad actor takes information off of your systems, whether it's a government system, a government contractor system, healthcare system, and they take it and they store it in their data centers. Doesn't matter if it's encrypted or not. The goal is, once they have a quantum computer that can crack encryption, that they're going to start cracking encryption very quickly. And that leads to vulnerabilities and threats. Why does this matter? Because it impacts everything we do today and every industry we do today, including logistics. There are more than 20 billion devices globally that will be impacted by encryption being broken. It doesn't matter if it's a car, plane, train, phone, computer, servers, networks, everything will be impacted once encryption can be broken. And what does this mean that encryption is going to be broken? So if you look at the white line, there's this thing that we use with classical encryption, where as you continue to make the encryption harder, that the time that it takes to break that encryption continues to increase to the age of the universe. But what they found is that with quantum computers, when you use modern encryption, which is taking two prime numbers, multiplying them together to get a bigger number, that doesn't change over time as you continue to make the number bigger and bigger and bigger. So in essence, you flatten the curve, and the time that it takes to break encryption goes from years and decades to minutes, seconds, days, or even weeks. So practically speaking, when that large fault-tolerant quantum computer is available, most of our existing encryption schemes are going to be vulnerable to quantum attack. So no longer will we be able to have Alice and Bob talk to each other, or General Smith and Airman Jones. That encryption will now be broken, and the communications will be in the open. And so what we need now is we need two things. One is quantum key distribution or quantum communications, as well as post-quantum cryptography. And I'll tell you a little bit about each of those. So quantum key distribution is a method where you have secure communications through either satellite to ground communications, fiber optic ground communications, or a combination thereof. And what makes it special is that anytime that there's somebody who's trying to get into your communications network, it actually eliminates the data that's being transited, and you cannot detect, or you cannot interrupt that communications. You can't take that information. This is sometimes called quantum cryptography. What I will say is that it's not endorsed right now by NSA, CISA, or NIST, primarily because you can do a denial of service attack, and you'll actually never get your communications through. But for short distances, very secure communications, this is something that could be effective. And what QKD, quantum key distribution, does is that it takes information, transfers it down, makes all of the encryption keys random, and enables you to connect things like government networks, banks, and other critical infrastructure using fiber optic cables or space-based communications. Not something that would be financially feasible for the entire world to do, but you could have it in small doses. And the one that is really even more impactful is a thing called post-quantum cryptography. It's also referred to as quantum-resistant cryptography. The US, our Five Eyes community, the French, as well as most of the industrial base, is starting to look at how do they migrate to post-quantum cryptography. And what is post-quantum cryptography? It's a new schema that's using different types of math rather than putting two large prime numbers together to create a bigger number. And since 2020, there have been a number of policies that have been put out by the White House, as well as the Quantum Computing Cybersecurity Preparedness Act, that has said that everyone must migrate to post-quantum cryptography. Whether you're a national security system, whether you are a part of the broader government ecosystem, financial systems, and others should be looking at doing this as well. And what does that mean? You need to create an inventory of what your encryption is, from your file systems, your APIs, your networks, everything that creates and has encryption. You have to figure out what it is, where it is, and what type of encryption's on it. And then you start to deploy and do pilots and see how it impacts and delays or has latency in the encryption. You figure out what your high-value assets are and what you need to protect most often, as well as first. And then you move into creating an entire suite of post-quantum cryptographic capabilities for the Air Force, for the Space Force, for government, for other institutions. So that you discover, you manage, and you remediate. So you discover your capabilities, you figure out what you need to do, and then you fix it. And so why does this matter for logistics? We need to protect logistics networks. We need to make sure that what's being moved and when, as well as what the supply chain looks like, are things that our adversaries don't know about. We also don't want them to know where things are stored, because that becomes a target, and when they're ordered, because that tells you what's limited or what's in low supply. We also need to have secure communications, relaying information about movement of troops and supplies, as well as things like protecting travel for flights, naval and surface vessels, and routes. DV travel right now is one of those things that's classified, or it's protected. This would be something that could be broken, or even the sensitive materials moved, such as nuclear weapons. We need to make sure that all of that is continually maintained and secure. Okay, and then the last thing we're going to talk about is quantum sensing. Quantum sensing, in particular, alternative position, navigation, and timing. The main challenge, as I talked about, is building a quantum computer related to technology. But one of the key advantages of quantum is that we can do things like quantum sensing today. Quantum sensing enables us to do things like global navigation without relying on GPS, and it can't be exploited by other jamming capabilities because of how the sensors are built, how they're put in place, and how they're used. And what we do is we take the quantum sensor and we take artificial intelligence and we marry the two together. And I'll tell you about that in just a second. So these are all the different types of applications that you have with quantum sensing. It can be everything from subsurface detection to semiconductor imaging to medical devices. In the logistics world, navigation is probably one of the biggest and most important ones that we have, as well as possibly subsurface detection. GPS is degraded on a daily occurrence. How many of you worry about GPS degradation, especially in a logistics environment? Just this last week, Russia is said to have believed to have jammed the signal of the UK defense minister's plane when he was flying in and around Ukraine and other places. The red areas on this map show where GPS was jamming on one day, on the 10th of October in 2023. And you can see that it's not just limited to the Ukraine-Russian areas. There's a lot going on around Israel and the Mediterranean, as well as on other parts of Europe. Interestingly enough, when you have GPS jammed, you have degradation when you have just the inertial navigation system in aircraft. And you drift 1,500 meters after 60 minutes of having your GPS jammed. As we know that if you drift into another country's airspace without knowing it, you could potentially be shot down or a target. So we need to make sure we keep people on track where they need to be. We also have the problem of spoofing. Spoofing is, it says I am one place, but I'm actually in a different place, which is almost more challenging and more dangerous than jamming. And so if you have an alternative GPS system that you can compare off of where the GPS is saying you are, as opposed to where the magnetic field of the Earth says you are, you can now see maybe I'm being spoofed or jammed. This is a look at where the Chinese have their position, navigation, and timing systems. It's their transmitters where they are jamming GPS. And you can see how far this reaches out. It reaches beyond the island chains, beyond Taiwan, beyond South Korea, and covering half of Japan. So if we were ever to get into a conflict with the PRC, we'd have to understand that this is what's going on in order to protect not only our people who are flying, but also those that are moving on surface vessels. And so what is something that we can do with quantum sensing? We can actually navigate using the magnetic field of the Earth. The crustal magnetic field of the Earth does not change. It is something that is there, it is always there. And NOAA and NGA, the National Geospatial Intelligence Agency, have done mapping of the magnetic field of the Earth. And it creates a map that looks like a heat map like you see on the slide. And what we can do is we can use a quantum sensor to detect the magnetic field over what we're flying, compare that to the maps that we know, and it creates us to have an ability to know in time and space where we're flying. What we do need to do, however, is create a combined AI and quantum capability, because we need to take out all of the extraneous noise in the magnetic field of the aircraft, the magnetic field and the magnetic signature of the phone in your pocket or the watch on your wrist, as well as all of the other systems that are in the aircraft. But once you subtract out that noise, you're left with that core magnetic navigation capability. This solution is unjammable, unspoofable, it's day-night, all-weather capable. So you no longer have to worry about whether or not you can see where you're going for visual navigation, or worry about GPS being jammed, because you're passively collecting the magnetic field of the Earth. The map's pretty cool. You can actually see land masses and things. I really like it. All right, so why does quantum matter for logistics? Many people think that quantum is a technology that is something that is so far out there in time and in capability, as well as in understanding what it can do, that they aren't considering it today as something that they should be thinking about. For logisticians, for leaders, for people who are even trying to do war planning, they need to be thinking about the future of quantum. One of the reasons why is the global investment for quantum is $36 billion and growing. It's predicted that in the next 5 years, it will probably be at $100 billion. Much of the technology is here today. The one technology that is still eking its way through is that quantum computer, but we're going from 433 qubits to 1,000 qubits, so we're doubling our qubit count very quickly. And then finally, many of the applications that are vital to logistics can be impacted by quantum technology. We talked about route optimization and supply chain optimization, using that quantum simulation, and then eventually migrating that to quantum computers. Being able to provide data, provide supplies, and doing it in a more cost-effective way is key. We can also develop new materials and batteries. If we can make the cargo that we're shipping, as well as the delivery devices that we're using, lighter, we can save money, we can save fuel. As well as looking at batteries. If we can now maybe use electric vehicles that can extend the range of what we're doing without having to rely on fuel and resupply routes, that could impact our ability to fight in wars and win wars. And then finally, we have post-quantum cryptography and quantum key distribution as a part of the quantum communications. We need to make sure that the data that we find valuable and important is protected, it is secure, even when it is unclassified. And oh, by the way, when it is classified. And then finally, quantum navigation. Having an alternative position navigation and timing capability that cannot be jammed or spoofed, and gives you a way to pull together a group of capabilities to enable us to know where in time and space we are navigating for safety of flight, safety of surface navigation, as well as understanding whether or not we're off our route for either understanding our fuel restrictions, as well as where we are in adversarial territory. All right, and with that, that's what I'd like to say about logistics. Logistics is the backbone of all military operations, as you all know. I don't have to tell you that because you're all logisticians. And quantum is a way that you can continue to improve your day-to-day operations as well as your future planning. Thank you.